Oh boy, okay. I have the first part of the physics simulation done. The movement step and the collision, finding the collisions. And oh boy, it turned out to be kind of bigger than I thought it would be. I thought it would be kind of concise because I would just have the collider versus the colliders and then circle versus the collider because and it ended up being like well, I rewrote the same code twice for the circles because it has to go from it has to flip some of the sides from positive to negative, so it's like it kind of needs to be done, but the code, it ended up being a lot of code. So what this does, so first of all, let's start up here. Actually, let's start, we have a game loop, so we update our game and this steps forward a tick timer, and we updated a fixed ticks per second, so this keeps our physics and game logic constant between devices. So whenever the tick timer goes above the tick step interval, it does a tick. And then we also limit the number of ticks per frame, so if it's really lagging, it doesn't cause it to lag more by trying to simulate like 1,000 frames if it starts falling behind. So then this runs the physics tick. So the first part of this is the movement step, and this loops through the fruit, steps the movement and angle forward based off the movement and angular velocity. Then this calculates also the new cosine and sine for the angle, and it resets the collision. We have a collisions array that stores the collisions that happen during a tick. And then we also have this repel X and repel Y, which is how much the fruit gets pushed back to solve the collision. So in the find collisions, we go through here and we do the collider. We solve two collisions. We do the fruit versus the boundary walls, and then we do the fruit versus other fruit. So the fruit versus boundary walls is done using like two planes, and it selects the closest plane. So when it finds a collision, it creates a new collision object. We use an object pool for this to limit allocations. The collision object has information about the collision, the X and Y, relative to the fruit that this collision is the part of. And then the fruit is the other fruit that this collision hit. And then the normal X and normal Y is the world normal. And the X and Y is relative to this fruit, but it isn't relative to the angle. So it's in like world space rotation, but local space position. So then we loop through fruit versus fruit. So to do collider versus collider collision, we loop through the points of each collider and test them against each collider. And then we average all of these collision points to get an average collision point, an average collision normal. And we also add up this repel X and repel Y, how much the object should be pushed back to solve the collision. And we also do, using this same part, we do circle versus collider. So this is just pretty easy. We just take the position of the fruit that's a circle and test it against the collider. So we have that collider A versus circle B, and collider A versus, or circle A versus collider B. And then when we have a collision, we average all of these, we add them to, we have two collisions, one for each fruit. So an A collision and a B collision. And these have like, each have their own local position, and then the normal is just flipped for one of them. So then we have circle versus circle, which is also just easy. It's just the distance or direction between the 2 points, the circles. And then finally, this is the part that I need to program the actual collision response. Right now I just apply the repel, so this solves the collision. But what we need to do here is now we need to add we need to change the velocity in response to these collisions that we've built up. So let me show you what we have right now though. So this is the watermelon. I have a test fruit, and you see I send it sideways. Doesn't change the velocity at all, it just keeps going into the side of the jar, but it shows you how it hits the side of the jar, it collides with it, and it just basically shows you the collider, the watermelon, is working against the jar. And then we could change the fruit to say a banana to show another shape. But yeah, now to have this work properly, we need to have it actually bounce off or change the velocity. The velocity is just changing the same when it hits the wall, which obviously wouldn't happen. Alright, let's get to it. Alright, here we have our velocity response. So this system I've designed to be pretty standard as most game engine physics engines. So there's friction. Each object has a physics material with friction or bounce. Bounce is how much an object goes parallel to the surface normal, and friction is how much it pushes when going perpendicular. And then how much force is transferred is based off the masses of the objects. So lighter objects push heavier objects less, and vice versa. So both these objects right now have one mass, and I'm just going to show you a quick demo of changing the mass, and then I'm going to go into how the code actually works. And this was a bit tricky. It always is making a physics engine. So I'm going to shift the pineapple mass to be 10. So now you can see it doesn't bounce off the banana at all. The banana also barely pushes the pineapple. And you can see there, since the mass is 10 to 1, it pretty much takes 10 bounces of the banana to reflect the velocity of the pineapple. And I have my physics energy function here. So you can see now the energy just went to 0. When both of the objects connect at the same time and connect to a static collider, all of the energy or velocity goes into the static collider, like these walls. And since the static collider doesn't move, the energy just disappears. So this is the situation where things just stop. This isn't completely realistic, of course, but this is good enough for me for my physics engine. I'm pretty happy with this. The main thing is, so far, is that the physics engine conserves energy. So you can see I have this physics energy function that calculates the total energy, the length of the velocity multiplied by the mass, the objects, and then added up. And you can see it starts at 3 and stays basically at 3 within floating point errors. So, alright, let's go into the code. So I actually changed this I changed the collision response a little bit. Hold on, I'm just pausing this. So before I was having two separate collisions, an A collision object and a B collision object, one for each object collided with. I decided when I went to go program this collision velocity response, I found it was way easier to just have one collision object and then store that in one of the objects and then just count the total collisions. So the reason why we need to account for the total collisions is that if an object hits two objects, you can't just put all of the velocity in both objects. It needs to be split between both. So the way we do that is by simulating it splitting the mass. So you can see here we divide the mass by the total collisions when we calculate the mass scale of the collision. So this way, when an object hits two objects, it splits its mass or velocity or energy between the two hits. And so this does have the issue of when we're colliding with a static collider, some of the energy goes into that instead of the dynamic, which of course it's static. It doesn't actually, the energy doesn't actually go into it. So there is of course losses where it doesn't conserve energy. I think it's good to be aware of where your physics engine fails or has those non-realistic situations. But for the most part, I'm pretty happy with how realistic it is. Friction and bounce work pretty much like you'd expect. I chose multiplying, so if you see here, I chose multiplying the bounce and friction to calculate the total friction. This lets, and then clamping it. So this lets you do stuff like you could have a very bouncy object of like 10 bounce, and that could multiply off like a 0.1 bounce object to make an actual full bounce of 1. Or likewise with friction, you can have a completely slippery object multiply by 0 and completely cut out all friction, even if an object has a friction of like 100. So that's why I like to do multiplicative. In some engines though, like Unity, you can see that they let you choose how the friction in the physics engine is calculated, whether or not it's multiplied, averaged, or summed. Okay, so for our physics velocity response, what we do is we want to change this old velocity based off all of our collisions. The collisions can be split into two objects, or two types: dynamic versus dynamic collisions, two rigid bodies versus each other. That's more complicated, of course, because we have to take into account both of the object's velocities. And then static versus dynamic, which you can see the code is way smaller, it's way simpler. We're going to cover this first. So the amount is the bounce amount, how much the velocity matches up with the surface normal of the collision. So you can see this is the dot product. So part of what made this physics engine so tricky is I wasn't using any vector library because it's JavaScript. It's not as efficient. It's most efficient to just write it out like this. So I've just written out all of the vector math here. So this is the bounce amount. If the velocity is against going the opposite direction of the surface normal, we don't do any calculations and we just copy the velocity as normal. Technically this collision shouldn't have happened, and it likely only happened because the object was pushed by some other object, and it's like in one of those situations where it's bouncing back and forth, jittering. So we just keep the velocity as usual and don't calculate. And anyways, when this is positive or flipped to the other sign, these math calculations don't work properly unless you flipped it to the absolute value. So to get, then this amount though is scaled by the velocity length, which we want for calculating it here because we're going to add it back to the velocity multiplied by the normal. So having it the same length of the velocity is useful. But for calculating the friction, we want it normalized from 0 to 1. So we divide the amount by the velocity length. So now this is like your usual dot product of the normal. So the friction, we calculate the friction multiplying the wall friction by the rigid body friction. So to calculate the friction, like the per frame friction amount based off of your delta time, you need to apply the exponent, or I don't know, put it to the exponent of the delta time. If you think about this, if it's 0 delta time, it's 1, there's no change. If it's 1, it's 1 second, then it applies the full multiplication of, so you can think of this as representing your friction as how much it multiplies over 1 second. So if it's like 0.5, it'll multiply it to 0.5 over 1 second. Whereas if you don't put this to the power of the tick step, doing 0.5 at say 10 frames a second would be 0.5 to the power of 10, which would end up multiplying it like way smaller, like 0.001 or something. So this makes things consistent and lets you just set a friction value that's independent of frame rate. So then bounce, multiply the bounce, clamp it to 1. So we multiply this amount by 1 plus this bounce. So if you think about it just at 1, if we look at this here, and you forget about friction, just pretend friction is 1. Vx plus Cnx times amount. This is like the vector reflect function being applied to the velocity. So we're pushing back with the normal based off this dot product amount. So it's like reflecting. So with amount at 1, this just pushes back the velocity and we'll just lose all velocity. But when bounce goes up and say it goes to 2, it'll push back and it'll actually completely reflect your velocity. And say like it bounces against a wall with an x normal, it'll flip the x negative. This math takes a little bit of thinking out to figure out, and it would probably make a lot more sense if it was using a vector library function and this just said reflect. So then we multiply all of these velocities by TC scale, which is our 1 divided by total collisions, because just to make it simple, I'm just averaging all of the all of the calculated velocities, and that's how we'll get our end velocity. There's technically there's some more complicated ways of calculating this that are more accurate, but for the sake of this physics engine, I'm happy with this and it works good enough. So now the actual complicated dynamic versus dynamic. A bunch of this code is the same, like the friction and the bounce. So that's why I already covered that down there. Don't really need to think about that. So it's mostly the same if you go and look at the main code here. The NFVX, NFVY is the new fruit velocity of this main fruit. And the NHVX and NHVY is the new velocity of the hit fruit that's from this collision object. So if you see here, the NFVX and FVY here with the amount smaller than 0, this is just like the static versus static collision. It's calculating it basically exactly the same way except for the bounce scale. If you see, the bounce scale is multiplied by the mass, because we have to take into account the mass scale. And then these the same force we take and we apply the inverse, the backwards force to the hit object. So it's like for each like forward force, we apply a backward force. And for that, we also scale by the mass scale, but we scale by the different masses. So I should cover, we have a few different mass scales here. So the main mass scale is this fruit divided by the hit fruit, and then the I mass scale is 1 divided by that. So it's technically the hit fruit divided by this fruit. Then we've got the clamped mass scale, clamped inverse mass scale, and this clamps it to 1 so that it can't multiply over 1. And this is so we limit the velocities in a lot of these cases. Like, it's not realistic for if you have a big heavy object, it doesn't go and hit a smaller object and just send it like going like 100 meters a second, like way faster, just because it's higher mass. It only pushes it as fast as it was already going. So that's why we limit that to 1. All right. So like I feel like explaining most of I wasn't going to explain all of this, but I feel like going through it is pretty important because the physics engine is a really big part of this game, and doing a full physics engine like this, the next thing we're gonna do is add rotation. There's not a lot of things that fully cover it like this, so I thought I think it's a very good thing to do. So with our mass scale, we use this to basically like scale the differences of the velocities. So if we've got like the 10 mass object, say we're hitting the 10 mass object and our mass is 1, so the mass scale is 0.1, then you can see here when we hit the other object, it multiplies our velocity by 0.1 because our mass is 1 to 10 of that velocity. And you can see here, this is pretty much the same vector reflection here, just with different scales. The bounce, instead of being scaled upwards, is scaled down. So basically when there's more bounce here, more of the force goes into here and less of it goes into here, and vice versa. And then with the inverse friction, it's the same. When more force goes into this, stays in this fruit, it doesn't go into the head. And then this right here is exactly the same code as up here, but being applied from the hit fruits side. So it's calculating that. So a lot of these things are flipped and negative because we're using the same normal and same perspective of the collision, but it's the different hit fruit, so we have to flip around a bunch of these signs. So that's why a few of these things are different. So that's like the same thing as there, just flipped around. So you can see like the C mass scale is here instead of here, and the CI mass scale is on the bottom here instead of on the top. So then down here, this is the big important part for the stability of the physics engine, the velocity, length, and energy conservation. So these functions need like a bunch of complicated differential equations to actually solve properly and create a stable system. So what we do is we go and we measure the length here of how much length of the velocity was taken out when we apply one of these collision responses. And then we look at how much the other hit object's velocity changed, and we basically make sure that the same amount of velocity that was taken out is put into the other one. So you can see here we scale up this fruit velocity based off of the hit fruit's velocity changed amount. So this is calculating the delta of the delta, so the difference of the two different. It's calculating the difference of the differences, multiplying that by the mass scale, and then we add that back to the normal velocity, so it change it to a scalar amount relative to itself, so that we can multiply the velocity by that, and that scales up the velocity to account for the length or energy that should go into it. And then we do the same thing here for the hit velocity. It's the same thing, just with the values changed around. So here you can see the target. This is the target. So you can see here the target is the fruit velocity length amount changed from its starting value. And yeah, without that, the physics engine becomes unstable and the objects just go faster and faster. Here, I'll show you that. Oh, wrong thing. So you can see here the physics energy starts at 3. And without that length conservation, it just goes straight to 0. Oh, because I commented out the wrong part of the code. So you can see now it's already gone down to 2.4, 2.3, So in some cases too, it also goes up, which is really bad for the stability. That can send objects flying. Yeah, so that you can see now the physics energy is just going down and down. So without this length energy conservation, it's not stable. It's very important. And now you can see the physics energy stays 3. And that is the main part of the physics engine velocity response and code. I would say this part is the main part of the physics engine, is handling how you exchange velocities and collide the two objects. And there's other ways to do this too, so this is definitely not the right way. All right, and then we just add these velocities scaled by the total collision scale. And I actually just realized a bug. This hit velocity shouldn't be scaled by this total collision scale. It should be scaled by the hit total collision scale. Like this. And this is the other good reason you go over and you explain your code. This is essentially rubber duck debugging. Can you guys quack for me? So the next final last thing we have to do is add in rotation. So the angular velocity and rotating the colliders. So it's going to be adding more code to the collider detection up here. What we're going to do is when we have these points relative to the collider, we're going to rotate that by each object's rotation, so we get the points relative to each fruit. And for the collisions, we need the points relative to both the fruit, the main fruit, and the fruit that was hit. So we're going to need to do both rotations. But that's all doable, and we're going to do that first, and then finally we're going to add in angular velocity, which I don't think is going to be that hard. We basically take these velocity vectors and we convert. When we start them out here, we take the points where the collision happened and we apply the angular velocity to them to get like a linear velocity amount that we just add to this, and then do all of our normal calculations. We get another linear velocity vector out, and we take that linear velocity and we check how perpendicular that is to the center of mass direction of the object. And if it's it's basically the dot product of the perpendicular direction. If it's perpendicular, we put all the velocity into angular velocity, into angular momentum. Yeah. And that requires a bit of length energy conservation from what I remember as well, because the length that you convert to a rotation, like when you convert the linear velocity to a rotation, the rotation is an arc and the linear velocity is a line, and they don't completely match, so you need to conserve that as well. That'll be the next interesting part of this. All right, let's add in rotation. All right, I've implemented rotations into the collision detection. So now we can see two rotating bananas. And when they hit each other, you can see there the collision detection's working. Like the banana is approximated with a capsule line, so it's not completely perfect, but it does look pretty good. You can see them bouncing around here. So the main thing I had to do here is just convert between local object space of the collider and the world space. So we basically just apply the rotation transform forwards and backwards when we sample the collider. And I had to implement the rotation for rendering. So the first thing in the rendering is we take the sine and cosine of the angle, and then we rotate the point using the sine and cosine. So this is technically 2D matrix rotation. And this SPCX and SPCY is the sprite center X and Y. So we got to make sure for this, the physics to be correct and matching up, the object rotates around the center of mass. So that SPCX and SPCY is the center of mass of the banana. And you can kind of see the center of mass is like right here on the middle edge of the banana. So that was a little bit tricky, making sure it's the right direction, and you got to apply the rotation to that sprite center offset. So just making sure all of that was correct was the first thing. Here is, you can see where I set the angle. So just to be clear, this angle isn't the same thing as angular velocity. You can kind of see when they rotate into each other there, they don't actually apply the force of the rotation. They're just rotating a fixed amount based on the time. So this is more like taking a static collider and rotating it. So to do the collider rotation, let's go up to a sort of easy one, the circle A versus collider. You can see we take this point on the collider, and now we have this 2D rotation matrix here, and we apply the inverse rotation. So we convert from the world position, invert it backwards to the local position. And that gives us, so then because these collider nearest functions are done with points relative to the collider, then once we get the normal back from that, we need to rotate that back with the non-inverse, the normal rotation, to get the world normal, because the normal that you get out of this collider nearest function is local, just like the points you put in. So that's basically the essence of doing the collider rotation, is converting between local and world rotation. And that's done pretty much the same thing here. We take the points from the collider and we apply the rotation forward, because we're converting from the local points to the world space points of the A collider, and then we take that point and we apply the inverse B rotation, so converting from the world space position to the local relative to B space, relative to the B rotation. And then that is what we feed into the B collider nearest, so it's all relative. And then of course we apply the normal, we apply the rotation back to the normal, so that the normal is in world space. All right. So I did all that first before angular velocity, because this kind of has to be all set up correctly and stable. It makes it easier to split things into stages like this, so you don't have bugs layering on top of bugs. All right, now for angular velocity. And here we have our physics system with rotation. So here none of the objects have friction. So you can see they're kind of slidey. And of course this is not perfect, but I'm very happy with it. And so I still need to rewrite the physics engine. So this took a lot of testing. The angular velocity was quite difficult. I had to completely rewrite all the energy conservation code. So what I'm doing right now is kind of a hack. I'm taking the whole energy across all of the fruits in the physics engine and system, taking the energy, and if there's too much after doing all the calculations, I rescale the energy and take it out. And this is a hack, because this is like, then objects can get velocity out of nowhere, and it's not the right way to do it. So to do it properly, I'm going to need to make a chain of what objects are colliding with each other and conserve energy just between those objects that are touching each other each tick or frame. But I thought I'm going to show off the what I've done now before I rewrite it. So you can see now it's not completely stable. The limes here are particularly tricky. Because they've got these sharp edges, they can intersect into each other and get stuck in each other. The good news is in the actual game, when these same fruits or shapes touch each other, they'll get combined into another fruit. So that's actually okay. But yeah, this, as far as I'm aware, is a pretty standard physics engine. Each frame, the fruits are pushed forward based off their velocity, angular velocity. We calculate if they're then colliding any other fruits. From that collision, we generate repulsion forces and the new velocities. Apply the repulsion here and calculate the new velocities. And then that's not completely conservative of energy. So then we apply energy conservation. And that's the part I need to rewrite now. And if you see, I have all of this uncommented, or commented code. And this is all the different ways I tested of doing the calculations. And what I settled on is pretty simple. I just add up the forces, convert them from linear to angular. And so if you remember a few minutes ago in the last video I made, I was doing the energy conservation here in the actual collision calculation, but once we get angular velocity and we actually get all these objects touching each other, the proper way to conserve it is to actually separate all of the touching objects into their own systems and scale back the energy that way on like a per system basis. So yeah, I actually got the angular velocity working pretty much right away. Like I was saying before, you just convert force that's perpendicular to the center of mass to angular velocity, but then that doesn't conserve energy. So conserving energy here in the dynamic versus static collider worked properly. So I thought everything was working good, and I went to apply that to the dynamic versus dynamic, and I realized that I could no longer conserve energy on what I was doing here. Is I was able to still, previously before angular velocity, I could conserve energy and just transfer the forces between the two objects because energy was conserved. But because it's no longer conserved here, and we can't conserve it until the way I do the energy conservation is you calculate the final resulting velocity after the forces are applied and scale it up after that. But if we applied these forces and scaled it up before, there's other objects that could be colliding with these same objects and applying forces. So just conserving the energy here and scaling it up isn't completely right. Like if you imagine you could have one object adding a force in one direction here that applies force, and it seems like this would have energy, but actually another object is colliding with this and applying a -1 force that averages out to 0, and it isn't correct unless you apply that energy conservation after all those forces are averaged out, like down here. So here is an example. I'll show it now with friction too. The objects sort of act like gears, sticking to each other with large friction. But you can really see the rotation works well. I did a bunch of tests with spinning the circles and seeing if they acted like wheels, and they pretty much do, and it all conserves energy. And that's pretty much what I'm worried about, is it being stable and conserving energy for this game. And the little bits of instability here with the collision still, I can solve. I'm only doing a single collision solver iteration, which is really bad, and it's running at 50 ticks per second. So I can make the physics engine a lot better just by ramping up that tick rate. And I'll probably end up doing that, but I'll start working on the actual game and see if we even need to do that. You can see here we got another set of limes stuck together. The question of whether or not two objects get stuck together is a question of how fast they're moving, how fast they get moved, and the shortest distance between the collider. So you can see here edges of the lime are particularly tricky, because if the lime moves, like this edge here you could say is probably only like 0.05 units. So if the lime moves more than 0.05 units a frame, this edge will just go through another object like another lime. And then once an object is inside another object, the collision doesn't get solved properly. It gets repelled inside. Sort of repulsions cancel each other out. So physics engines are tricky is the general consensus, I think. So anyways, I'm going to rewrite all of this now and clean it up and add in the per collision, I don't know what to call it, like per touching object energy conservation. Yeah, then I'm very excited to get that done. Then we'll actually work on the main game.